In this module, I'm going to review measures of model performance and the problem of overfitting. When we talked about measures of performance in the context of explanatory models, we focused on the beta coefficients and p-values for individual predictors. For predictive models, we care less about the performance of individual predictors and more about the performance of the model overall. I'm going to talk about metrics that measure a single model's performance, as well as metrics that are used to compare two models. The standard metrics used for evaluating predictive models are goodness of fit, discrimination, calibration, and reclassification. Reclassification is the one that's used to compare two different models. I'll go through each of these now. Goodness of fit tells you about the overall fit of the model. The idea here is that you want to minimize the distance between the observed outcomes and the outcomes predicted by the model. For linear regression, we typically talk about the root mean squared error and the R-squared value. The root mean squared error just gives the standard deviation of the residuals. This tells you on average how big are the residuals, how far are the observed values from the fitted line. You want this to be small. The R-squared tells you how much of the variance in the outcome is explained by the predictors in the model. Obviously, you want this one to be as high as possible. In this course, we've talked about the -2 log likelihood in the likelihood ratio statistic. We use that actually to compare nested models. So in fact, to look at overall model performance, we usually instead look at the AIC, which is directly related to the -2 log likelihood. So remember, the -2 log likelihood comes out of any model where we're doing maximum likelihood estimation, such as a logistic regression. And when the probability of our data is high, the -2 log likelihood will be lower. So we actually want a smaller -2 log likelihood. We can't directly compare log likelihoods from two different models that have different numbers of parameters, however. And so all the AIC does is it adds a penalty for the number of parameters in your model. That penalty is equal to 2 times the number of parameters in your model, and that includes the intercept. So imagine you fit a model for an outcome and you have 5 predictors in the model, plus you of course have 1 intercept. Then you are going to have k parameters in that model. And let's say the -2 log likelihood value comes out to be 252. You're going to add a penalty of 12 to that for all those predictors you have in the model, giving you an AIC of 264. Now imagine that you fit a model for the same outcome, but now you use 3 predictors only. So now you'll only have 4 parameters in the model, including the intercept. And of course, the -2 log likelihood is going to get worse. You have less things in the model, so probably that -2 log likelihood is going to go up. But your penalty is less because you only have 3 predictors. So here our penalty is only 8, and we come out with an AIC of 263. You're going to pick the model with the lowest AIC, here the second model. And the BIC is actually similar to the AIC. Just to illustrate goodness of fit, here's some continuous data that I generated. You can see that if you look carefully at the points, there's a little bit of a curve to to those points. So if I fit a straight line, a linear regression, I'm going to be a little bit off. There's going to be a fair amount of distance between the points and the line. In other words, my root mean squared error is going to be higher than it needs to be. However, if I recognize that there's a curved relationship and I fit a nice smooth curve here to those data, you'll notice that my root mean squared error goes down. The distance between the point and the line goes down. So that's a well-fit model. You can also have something called an overfit model. In an overfit model, you're putting so many parameters into the model that you're basically fitting a little curve to each one of these individual points. So like this little minor curve here is fitting to this one point. What you're really doing here then is fitting the quirks or the noise in your data. Your root mean squared error is going to look awesome, right? You're going to have very little distance between the line and all of these points. But this is an overfit model. If you take that model, which is basically fit to the particulars of the people in this sample, and you apply it to a new sample, it's going to have terrible predictive ability. We're going to talk about a little bit more about overfitting later, but you can see why you would want to include a penalty in your measure of goodness of fit for the number of parameters in the model. Moving now to discrimination. Discrimination is just what it sounds like. When you have a binary outcome, It's the ability of the model to distinguish between people who get the outcome and people who don't. If discrimination is good, so what we are looking for is that our logistic regression model will give higher predicted probabilities for people who have the events than people who don't. And the specific statistics that are used to measure discrimination are, we've already talked about the area under the ROC curve, which reflects sensitivity and specificity. And in a minute, I'm going to talk about something called the C statistic. That turns out to be exactly equal to the area under the ROC curve. But let me give you an example of a classic risk prediction model, the Framingham risk score. This is a predictive model that attempts to predict one's future risk of heart disease, specifically a heart attack or a heart-related death. And the risk score is based on classic risk factors for heart disease, such as age, sex, smoking, blood pressure, and cholesterol. If someone gets a greater than 20% risk, that's considered high risk, and those patients should be treated more aggressively. And this just shows an actual scoring sheet that a clinician could use to calculate a patient's Framingham risk score. There's probably kind of an online app that you could use on a smartphone nowadays, but how this works was if you were a patient age 50 to 54, you'd get a 6 right off the bat just for your age. If you have good cholesterol, then maybe you get 0 points for that. Maybe if you're a smoker, you're going to get 4 points for that. Maybe your blood pressure is good, so you get 0 points for that. And then maybe you have too low HDL, so you get 2 points for that. So then you add those up. That's a total score of 12. So you come over here and say, oh, well, somebody who has a score of 12, their 10-year risk of heart attack or heart-related death is only 1%. So that person would be considered fairly low risk. Here's the ROC curve from a particular study which applied the Framingham risk score to some men and saw how well did it discriminate people who got heart disease and people who didn't. And it does a pretty good job. The area under the ROC curve here is somewhere in the high 70s. As we've talked about, the ROC curve reflects the sensitivity and specificity of different cutoffs of the predicted probability. But what exactly is the C statistic? The C statistic is the probability that a randomly selected case will have a higher predicted probability, say from your logistic regression, than a randomly selected non-case. So if you have a C statistic of 80%, that means your model gets the ordering right, gives the case a higher predicted probability than the control 80% of the time. And of course, we're looking for a value of 1, that would be perfect discrimination. A value of 0.5 indicates no better than a coin flip. How do you actually calculate the C statistic? So to calculate this measure, you look at all possible pairs containing one case and one non-case. If I have a study with 50 cases and 50 controls, all possible pairs of those 50 cases and 50 controls would be 2,500 possible pairs. So imagine that you go through and you look at all the possible pairs and you tabulate how many of those pairs is it the case that the predicted probability from your, say, logistic regression is higher in the case than in the control. Maybe you calculate that, well, hopefully let the computer calculate that for you, and you find that in 2,000 of those possible 2,500 pairs, the case indeed has a higher predicted probability than the control. Your C statistic would be then 80%. But let's say it's only in 1,250, about half of the pairs, that the case has the higher predicted probability than the control. Well, then you're not doing any better than a coin flip. You're not doing any better than chance, and your C statistic would be 50%. And again, this will come out to be identical to the area under the ROC curve. The C statistic does have some limitations. The C statistic is only based on rank ordering. You can get a perfect C statistic if your cases always have higher predicted probabilities than your controls, even if the predicted risk doesn't actually match the absolute risk of disease in your population. So if your model says a male smoker is going to have a predicted chance of getting heart disease of 25%, that model might have great discrimination, but maybe male smokers really only get heart disease 12% of the time. So that absolute value for the predicted risk might be off. Another problem with the C statistic is it's an insensitive measure of improvement in model accuracy. If you want to compare two different prediction models, maybe a Framingham risk score model, and then you add something to that model, like a fancy new biomarker, If you compare the C statistic between those two models, it might not budge much, even if that biomarker that you're adding does have some predictive ability. So it's insensitive. Instead, we're going to use something called reclassification statistics, which I'll show you later. As I mentioned, your C statistic may not truly, you might have a good C statistic, but your predicted risks might not actually reflect the absolute risks, and that's why we need calibration. I'll talk about calibration in a minute. Just to illustrate how much power you need here to budge the C statistic, this is a simulation that shows if you have one binary predictor. So imagine you're fitting a logistic regression model and you have one binary predictor in that model. If the association between that binary predictor and the outcome corresponds to an odds ratio of about 3, your area under the ROC curve is actually not going to be that good, even though that's a pretty strong association. We don't get odds ratios of 3 very often. In fact, in order to get really good discrimination, you have to have odds ratios in the realm of 9, which we rarely see for traditional epidemiologic risk factors. So a single binary risk factor has to be extremely, extremely associated with the outcome to correspond to a good C statistic. And here's an example where researchers ran a Cox regression model to predict death or major cardiovascular events. And they ran this with a model which they used the Framingham risk score, traditional Framingham risk score. And then they did a second model where they added some biomarkers, a panel of 10 biomarkers. They're calling it the multi-marker score. If you look at the ROC curve, here's without biomarkers and with biomarkers for death. Turns out the area under the ROC curve went from 0.80 to 0.82, so not a huge improvement. And similarly, for major cardiovascular events, it looks hardly different at all, but it went from 0.76 to 0.77, so just a small improvement. The researchers concluded that the addition of the multi-marker scores didn't add much to the conventional Framingham risk score. But a letter to the editor pointed out that if you applied this same logic to any of the traditional risk factors, blood pressure, cholesterol, in fact, if you put those markers in and out of the model, compared a model with blood pressure to a model without blood pressure, for example, that also wouldn't budge the C statistic much. So these established risk factors wouldn't pass muster. And this graph focuses solely on adding CRP, this is a marker of inflammation, to the traditional Framingham risk score. In this study, they show that, in fact, adding CRP did nothing to the area under the ROC curve. It remained at 81%. But that didn't mean that CRP wasn't without predictive value. So look at this graph here. What it's showing you is they took a sample of people, and at baseline, they calculated their Framingham risk score using just the original model. And people got classified as 0 to 1, 2 to 4, 5 to 9%, and greater than 10% risk. Then they followed them for 10 years, and they observed what actually happened. How many people in each of those risk groups actually went on to develop cardiovascular disease? For example, these people were predicted in this black bar here to have a 10% or greater risk of cardiovascular disease, and indeed 12% of them went on to have cardiovascular disease in the next 10 years, so it did a pretty good job. But notice when they stratified on CRP, low, medium, and high CRP, that CRP does something, because that same group, the greater than 10% risk group, when they had moderate CRP rather than low, had a much higher risk of cardiovascular disease. So CRP seems to have some predictive ability, but it's not picked up in the area under the ROC curve. And what we just saw in the last graph starts to get at the idea of calibration. Calibration asks, how do the predicted probabilities of the event compare with the actual observed risk? If you have a binary outcome, the observed risk will be the proportion of people in a particular risk group who go on to develop an event. If you have a time to event outcome, to get that observed risk, you're just going to use the observed Kaplan-Meier survival probability. Those will be the observed risks, and you can compare them to the predicted risks that you got from your model. That's calibration. The specific statistics we're going to use to do calibration is called the Hosmer and Lemeschau test and calibration plots. But the general idea is observed versus predicted. How close do we come? This graph illustrates this nicely. These are two theoretical risk prediction models. They're not real. You can see they're it's a made-up example. But both of these have great discrimination. And you can see that because in both cases, category 2 indeed has a higher risk than category 1, and category 3 is higher than 2, and so on. So it gets the ordering right. And that's the same over here in B. The ordering is correct. So great discrimination. But only graph A shows good calibration. In graph A, let's say this bar here is a 25% predicted or observed event rate. Well, the predicted rate, the black bar here, had a 25% risk of disease, and in fact, observed was just a little bit above that, maybe 26%. So good calibration, those are very close. Over here, however, the predicted risk was something like 26%, but the observed risk was much higher, maybe 33%. So a much bigger difference between observed and predicted means the calibration is not as good. This is showing you calibration for the Framingham risk score. I already showed you the ROC curve for this particular data set, but you can see the calibration was pretty good. In most of the cases, the observed and the predicted values are actually quite close. How do we formally evaluate calibration? The formal test that we might use is the Hosmer-Lemeshow test. This is a formal test of the difference between observed and predicted. For the Hosmer and Lemeshow test, the null hypothesis is that the observed and the predicted are going to be close together. And so we're assuming actually that we have a good model that's doing well, that we have good calibration. If we get a significant p-value, then if we reject the null hypothesis, that's going to say that we don't have a good model, that our model is poorly calibrated. A non-significant p-value, we don't have any evidence that our model is poorly calibrated. And this is just a chi-square test. We're specifically going to divide up our data into 10 risk categories and compare the predicted from our model number of deaths. We're going to look at counts rather than risks because it's a chi-square. So the count of predicted deaths in, say, strata 1 compared with the actual observed number of deaths in that strata, or whatever the outcome would be. And then we just do a typical chi-square, observed minus expected squared over expected, sum that up. This is going to be a chi-square with 8 degrees of freedom. In this case, it doesn't come out to be significant, so we don't have any evidence that our model is poorly calibrated. We can also do what's called a calibration plot. This is just a scatter plot of the observed and predicted probabilities for all risk groups. Here we have 10 risk groups. We are hoping that all the points will fall on the identity line. This is a line with an intercept of 0 and a slope of 1. That would mean perfect calibration. You can see that the points are not perfectly on the line. It's not terrible, though. So what you would do is you would fit a linear regression line to these points, and then you would compare the slope of that line to a slope of 1. Finally, as I've told you, comparing C statistics between two models is not a great way to compare two prediction models. We instead use something called the Net Reclassification Index, or the NRI. The idea here is you want to take an old model and a new model, and you want to compare them and see how good does the new model do at correctly reclassifying people, taking somebody who does go on to have the event and giving them a higher predicted risk. That's what we're looking for. I'll go over this now more formally. The NRA focuses on either the people who have had events or don't. So you now know who went on to have events and who didn't. And what you're going to do is you're going to compare the old model to the new model. And if the person actually went on to have an event, you're hoping that your new model would have given them a higher predicted probability than your old model. So you're hoping that they're going to go up in their risk strata. So if they were in risk strata 2, they're going to go up to risk strata 3, for example. The new model will be doing better if it moves those people up because those are the people who actually had the disease. And you're going to also look at the people who didn't have disease. The people who didn't have disease, you're hoping that the new model will downgrade them, will give them a lower predicted probability of having the event. And the NRI combines all of this into a final probability, and I'm going to show you how to calculate that with actual numbers in a minute. This is well illustrated in a little table, though. So here we have an existing model. That model was used to classify people into 4 risk strata. Say this could be the Framingham risk model. I'm going to look just at the people who had events. We are hoping that they will get a high predicted probability of having the event because they actually are the ones who went on to have events. This is the classification via the new model. Maybe you've added a CRP or some other biomarker. among the people who have had events, if they don't change risk categories, then that's a wash. But if you've had an event, you want the new model to classify you as having a higher risk. So you want your risk category to go up. So for example, if somebody who has the event was originally in the 0 to 5% risk category and your new model puts them in the greater than 20% risk category, great, your model's doing well. Your new model's doing well. You don't want people to be put down, so that's going to penalize you. Among the people who do not develop events, you want them to go down. You don't want them to go up. And the NRI is going to quantify how many people go up and down. So let's put some numbers to that. Here's an example where they were comparing the Framingham risk score with an additional biomarker, which is your total cholesterol to HDL ratio. You want that to be low. If you use the old model to classify people in these different risk categories, there are 133 people who had events. So these are among the 133 people who had events. And you can see that a lot of people did not get reclassified in the new model. They got the same classification, the same risk strata in both models. But there were some people who went up. So among the 133 who had events, 4 were reclassified from a 5 to 10% risk to from a 0 to 5% risk to a 5 to 10% risk. 15 went from a 5 to 10% risk to a 10 to 20% risk, and so on. So we have everybody above the diagonal here went up. There was 27 who the new model reclassified them as having increased risk. The model also put some people down that it shouldn't, but that was only 14 of them. Our total N here was 133. So if you were to subtract, the net correctly reclassified turns out to be a percentage of 9.8%. And if you look at those who did not have events, that's 1429 without events, you want them to go down and not up. Well, 177 went up, but more, 236 went down as they should. And again, you can calculate the percentage of those out of 1429. So the net correctly reclassified turns out to be 4.1%. So you do better on 13.9% of people, the sum of these two. And that was a statistically significant NRI. The NRI does have some limitations. For one thing, if you aren't going to treat patients differently, if they are classified as having 5 to 10% risk instead of 0 to 5%, then moving a patient between these two categories has no actual clinical benefit. So if these risk groups are kind of arbitrary and not clinically meaningful, a good NRI might not mean a lot. The integrated discrimination improvement is the continuous version of the NRI, and it doesn't have any need to arbitrarily classify people because it uses the predicted probabilities from your model. So instead of looking at specific risk strata, it just takes among everybody who had events, what was the average predicted probability from your old model among those people versus the average predicted probability from the new model? And you want, of course, the predicted probability to go up. So you want this to be positive. For those who have not had events, you want their predicted probability to go down. So that's why we're subtracting here. You want this here to be negative, and a negative times a negative will make a positive. So you want to have the predicted probability in the new model be less than the predicted probability in the old model. But similar idea to the NRI. This just shows that the NRI and IDI are indeed more sensitive measures of model improvement than the area under the ROC curve. So somebody compiled a bunch of cases to compare those different statistics. You can see an example here where adding some genetic markers, the area under the ROC curve stayed at 80%, but the NRI or IDI did show a significant improvement for those genetic markers. And there's lots of examples of that in this table. We'd like to see predictive models report goodness of fit, calibration, and discrimination. But here somebody's done a search of the literature to see how well we're doing on this. And they found that in 68% of cases, the authors did not report a calibration. In 27% of cases, they did not report discrimination. Very few actually reported overall performance measures. So we could do a little bit better in our reporting of prediction models in the literature.